So the topic of this talk is about the use of lichens as biological indicators of air quality. And first of all, I had to show this graph. This is a graph about the use of the word biomonitoring, biological monitoring, which can be found in a very well-known library of scientific papers, Scopus. So you see that from the 70s, the term biomonitoring has risen in importance until now, you see, and it's increasing and increasingly used. So biomonitoring, biological monitoring, I tried to repeat many times this point, is very, how to say, on fashion, very useful, very studied by researchers. So now let's try to understand why. Well, I like this slide very much because it's an introduction to biomonitoring, to the use of living organisms for monitoring the quality of the environment, regardless if they are plants, animals, or fungi, or whatever. And the use of living organisms to check the status of the environment is well known. For instance, miners, they were well aware that using the small cannery, because the cannery have a very fast breathing ratio, so they breathe air very, very fast, much faster than humans. And so if there is a poisoning gas in the mine, the poor cannery was the first to die, to indicate to miners that it was the time to leave the mine. And this is all times, but I don't know if you remember that in 1995 in Japan, which is probably the most technological advanced country in the world, in Japan there was a terroristic attack in the tube, in the underground, and with the release of a poisoning gas. And how people, those technological people in Japan, checked if the air in the tube after some days was breathable, was good to survive. So if there is no risk, there was no risk again inside with the cannery, because they have all the device to measure anything, but when you don't know what you measure exactly, you just need to check the answer, what is the effect, the biological effect of an living organism. So that's why biomonitoring, going back to the slides from the growing interest in this world, that's why biomonitoring is still very, very important, absolutely necessary to maintain the information about the status of the quality of the air that you breathe. And it's also very important because if we check this graph, we see that normally we have a source of emissions, normally a chimney, and we have a sensor of devices measuring what is escaping from the chimney, so-called emissions in the atmosphere. In the atmosphere, we have the transfer and the transformation of the pollutants of what has been released from the chimney, and is transformed into emissions. Emissions, which is what that can be measured by normal instrument devices that measure sulfur dioxide, nitrogen dioxide, PM, and so on and so on, they cause effects on living organisms. So if you stop to measure the emissions at the level of the device, you have monitoring. If you measure the effects on living organisms, you have biomonitoring, biological monitoring. And why biological monitoring is very important? Because it's simple to understand, because it's clear. Because if you go to public opinion, to politicians, and you say, look, for instance, lichens are dying, and lichens can reflect, they are much more sensitive than humans and can reflect, like canaries, the state of the art in a while. So people can understand there is something wrong and press about politicians that can act to change the regulation, which in turn can be more strict and change the rules for the emissions and close this circle. That's why this is very important if you do biomonitoring research. Why lichens? What are lichens, first of all? What is a lichen? Lichens can be found in any botanical textbook, even for children. It's the most famous example of symbiosis. It's a symbiosis between a fungus called so lichens are a symbiosis between a fungus, technically known as a mycobiome, and an algae or a cyanobacteria, which is called photobiome, the partner which is doing photosynthesis. And you see here, this is the fungus, and this is the algae. And you know, algae have the capacity to do photosynthesis, which is the mechanism that allows the storage of carbon dioxide from the atmosphere into sugars through the use of the energy from the sun. And this is a slide showing how lichens can be seen on a tree trunk. When this is a slide at the simple optical microscope, very rough slides of a slide showing the fungal hyphae, the cells of the fungus, and the algal cells. You see the algae here, the green one. This is how a lichen is from the outside, and this is how a lichen looks like from the inside. And this is a nice image captured at the scanning electron microscope in false color, showing the structure of a so-called foliose lichen, which can be seen the algae very nicely, the green spheres. These are algae, green algae. You see an upper cortex, and then you have the algal layer, like leaves of higher plants. Then you have the so-called medulla, which is made up by hyphae from the fungus, and the lower cortex. And then there are sort of roots, which are called rhizines, but these structures, so-called rhizines, are not for taking up water and nutrients from the substrate, but just to anchor it to the substrate. And this is a cross-section of a foliose lichen, typical structure of a lichen. And if you see, normally I show this slide to see that there are many, many cases in nature showing the same solution facing the same problem. You see, one part of this slide is made by lichen, and the other part is made by a vascular plant. One picture is Usnea, a lichen, and the other, this is a lichen Usnea, you see, together with other lichens, and this is still Lancia usneoides transplanted. You see, this is attached to a tree for biomonitoring purposes. You see how similar are these two very, very different organisms belonging to different reigns, kingdoms, to different kingdoms. So very, very different from an evolutive point of view, but very, very similar in the structure, solving the same problem in the same way. So why lichens can be used very profitably in the use for biomonitoring of air pollution? Because they have no roots, they have no cuticle, they have no stomata to regulate the gas exchange. So they are very, very dependent on the atmosphere for nutrients, like spongy, which absorb anything that is in the atmosphere. So if the atmosphere is polluted, they absorb also the pollutants which are present in the atmosphere. And this is done over the whole talus structure, over the whole sample, let's say. And who was the first, basically, showing that there was the possibility of using lichens for this purpose, to check the quality of the air? It was a Finnish botanist called William Nylander. You see the date of birth and death, and you see that he has finished his life in Paris. This is very important because he was very famous for his last part about lichens, of course, for this last part in Paris, because he lived here, and this is death until the very end of the 19th century. And he wrote a famous, very, very famous article in 1966 about lichens of the Jardin de Luxembourg in Paris, a park in Paris. And he realized that in this park, this paper is in French, this is how it's written, lichens give, at their way, an indication of the quality of the air. So realized at the end of the 19th century that lichens were more abundant in places where the pollution was less, and less diverse, less abundant in places where there was more pollution, until that and the total disappearance of lichens, so-called lichen desert. So it's very simple that we can use lichens as sensitive indicators to estimate what? The effects, the biological effects of pollutants, the comprehensive effects at the biological level. How? Simply measuring changes at the community level, as done Nylander at the end of the 19th century. Very simple. And the first, let's say, organized, you see, 1 century later, 1 century, I give back, you see, 1966 and 1866, 1970. 1 century later, we have the first milestone in use of lichens for biomonitoring of air quality. It's a very, very famous, published in Nature by Oxford and Rose, about a qualitative, not quantitative, scale for estimating sulfur dioxide air pollution in England and Wales by the use of epiphytic. Epiphytic means tree inhabiting lichens. This is a very, very famous paper, and has been the ground, the base for many methodological research on this topic for many years. And the main point is a scale based on the assemblages present on the trunk at the side. So you have to go and check the assemblages based on the presence or absence of several indicator species. And based on this mix of lichen species, you have to give a judgment about the pollution zone, from very, very polluted, where only this very unsensitive, very toxic tolerant algae can survive, until places which are defined as pure, with very, very sensitive species like this Lubaria, Spannaria, Usnea, etc., species. Now, of course, this level of air quality by sulfur dioxide are very, very high, at least in Europe. Everything more or less is below 10 microgram per cubic meter as an annual mean. But perhaps these values are still very, very useful in places like India, where there is a high load, a high pollution by sulfur dioxide. So the use of lichens can be very useful for monitoring the quality of the air. Then at the same time, still in 1970, you see, in the same period in the other part of the world, in Montreal, Canada, other two researchers, LeBlanc and Desluver, suggested a quantitative index for establishing the relationship between industrialization and the distribution and growth of epiphytic lichens and mosses in this case. And they suggested the use of a so-called index of atmospheric pollution, called IAP, index of atmospheric pollution. And this index is quantitative because it's based on the number of the species that are present at the site, their abundance in terms of coverage and frequency, and a specific coefficient of toxic tolerance, of tolerance to pollutants of each species. So in this case, it's a qualitative for estimation of sulfur dioxide, and this is quantitative for the estimation of the overall air quality of atmospheric pollution. It's reverse, but the same at the side. And of course, the winner at the end was the index of atmospheric purity, as I will show in the next slides. So the index of atmospheric purity is simply based, that was formulated by LeBlanc and Deslouver, by this formula, where for each species there is the need to establish a frequency measurement as a measure of abundance, and to establish this Q value, which is the toxic tolerance value for each species. They establish the toxic tolerance of a species in a very simple way, because if a species is typical of unpolluted environments, normally it's told that the species should have many species living together, and the opposite for species living in polluted environment where only a few species can survive. So they establish this toxic tolerance coefficient as the mean number of companion species of the given species, Q multiplied by F, the frequency of the species. And then the very final step of this process in establish a very strong method has been done in Switzerland by an equipe of researcher from the University of Bern, led by Professor Klaus Ammann. And in 1987, they published this very, very famous paper about the correlation, a multivariate correlation of deposition data of 8 different air pollutants with the Lichen data collected through the index of atmospheric purity method in Switzerland. And it was very, very important, this paper, because it influenced all the history of this, the use of lichens for monitoring air quality in Italy, Germany, and the whole of Europe and the end. I have the pleasure and the chance in 1989 to spend 1 year as I was a young fellow as a postdoc at the University of Bern with Professor Klaus Ammann. It was really an enrichment for me to stay with him and with his group from almost one year. And what was the Swiss method? This method was based on the use of a sampling grid to have a quantitative measure, and to measure the frequency of the lichens. How? Just simply counting. It's a very, very simple method. Counting how many times out of, in this case, 10, we will see there are other grids, how many times out of 10 a species was present in the grid. It's very simple to measure the frequency. The Swiss method was based on placing the grid on 50% of the tree trunk, and should be placed in the place of the ball where the frequency of where the lichen cover was highest. So there is a certain subjectivity in placing the grid in the place of the other of the tree, and especially the area, the surface that was sampled was never the same, because it was based on the diameter of the species at rest height. It has to be placed at 1 meter more or less. Yes, 1 meter, between 1 and 2 meters from ground. So in Italy, you see, after 2 years, there was a slight modification to this method suggested by Professor Nimis to use a grid with a fixed size of 30 per 50 centimeters, divided in 10 rectangles in this way. In this way, the method was a measure of the biodiversity of the epiphytic lichens on the tree based on the sum of the frequencies of all the species that were present within the grid. So we had to go on a tree, place the grid, and then start counting the frequency for each species that are present on the tree. For each species, each one, the frequency is a number ranging from 1 to 10. And then at the end, you had to sum up the frequencies for all the species found, and that is the index of biodiversity, the index of biodiversity, in this case, of lichens. So the name has been changed as index of lichen diversity, which is more stronger, let's say, in this way. It was a period that in the 90s that we were starting to speak with enthusiasm about biodiversity after the Rio meeting, and it was enthusiastic to start with a stronger statistical approach, because if you remember here, you had to place the grid as a fixed size, but you still have to place it in the side, on the part of the ball with the highest lichen cover, which is a subjective estimation. You cannot be very precise. So this stronger statistical approach was simply based on dividing the grid in 4 layers into 4 subunits of 10 per 15 centimeters in this way. And the 4 subunits are to place permanently at the north, south, east, and west cardinal points on the tree at 1 meter from ground, precisely. So everybody can go on a tree and everybody knows what to do and knows where to place the grid. The method is the same, just go and count the frequencies, which are from 1 to 5 per 4 units. So from one species, it was from 1 to 10 here, now it's from 1 to 20. This is the simple change. This is the last version, the last modification of the index of lichen diversity, which is still on use now for measuring the frequency of the species. And this method has become, from a few years, an European standard, has been normed by the European agency for the standard, general standard, for measurement, for monitoring the ambient air biomonitoring with lichens, assessing epiphytic lichen diversity. It's a standard, European standard method for assessing the diversity of epiphytic lichens, which is in some way related to the quality of the ambient air. And another milestone published in 1997 in Nature about the use of lichens and air quality is another jump in advance, because this is a clear indication that there is a nice correlation between the biodiversity of epiphytic lichens and the incidence of lung cancer mortality. This is the Veneto region of Italy. Here you can there is Venice, or you know Venice. And of course, the proxy is air pollution. With lichens, we measure the pollution of the air, which in turn causes lung cancer. So measuring the diversity, the biodiversity of epiphytic lichens, we can have an indication of the risk of people breathing this polluted air to get lung cancer. This is a very, very famous paper published in Nature. It's very easy to be found by Cislaghi and Nimis. And this is very important to establish this connection between the use of bioindicators and health, public health. And there are several possibilities for doing research about the use of lichens as bioindicators. For instance, you can monitor one area, this is one town in Italy, and we have repeated the monitoring several times from 1993 to 2000, you see, and the colors are clear to understand this is the worst lichen desert and this is the best situation. You see that from 1993, the situation has improved a lot, really a lot. And you can measure the progress when you do something, try to improve the quality of the air. In this case, it was realized the connections to methane, the natural gas for domestic and public heating. It was a great improvement in the situation, and just in a few years you see the dramatic changes, the dramatic amelioration of the quality of the air. If you stop using diesel and coal for heating. And this is in Italian, apologies, this is one of the most famous newspapers in Italy, and it's a title reporting, you can translate using Google Translator or other, if you want, the reporting the use of lichens in forensics studies. Very, very important forensic studies about the air pollution by an oil plant, a coal plant, and a steel factory, the biggest steel factory in Europe, which is called Ilva from Taranto, another coal power plant in northwest Italy, and another oil power plant in northeast Italy. In all these cases, the the proof of the pollution of the air was based on the use of lichens, which are very sensitive to air pollution. This is written here. Lichens are, because are sensitive plants, sensitive species to air pollution. And so the point is that, of course, this is formulating the form of the question. The answer, of course, is yes. This is one paper which is open access, so you can pick it if you like. May the diversity of epiphytic lichen be used in environmental forensics? Of course, the answer is yes. If the research is done with certain very, very strict criteria, if the aim of the topic is explicitated, if the error of the study, the uncertainty of the study is specified, lichens can indeed be used as bioindicators and can be used in forensic cases. And this is very, very important. Now in Italy there are this forensic cases based on lichens. This is very, very, very important for the development of biomonitoring studies. Another important point which can interfere with what I've said so far is another totally different type of pollution, because until in the 70s, when the 80s, and even the beginning of the 90s, the main pollutants, the overriding pollutant was sulfur dioxide, which is very phytotoxic and can kill the lichens. Then we started to experience another type of pollution by nitrogen, nitrogen causing eutrophication. This is a model, now it's updated because I used this slide only 20 years ago. And the situation, you see, there was no projection, no positive projection, no real good improvement across the years. And indeed, the situation is exactly more or less like this. So nitrogen pollution has not improved in Europe. And what is the cause of atmospheric nitrogen that cause pollution? Mostly by agriculture, by animals. And another source of pollution is the industrial production of compost by the organic waste from urban, from cities, from citizens. This is a huge source of ammonia in the air. There is ammonia, in times transforms into ammonium. Ammonium can cause eutrophication of the bark. And this changes dramatically the composition of lichen species, lichen assemblages on the trunk. You see, this is a study we have done around the source of ammonia. It's a compost facility in central Italy, where I live. You see that we have measured the concentration of ammonia in the atmosphere that were in the range 40, 100 micrograms per cubic meter, and moving away, you see here, the concentration dropped really from 4 to 8 micrograms per cubic meter in a very short distance. And then the a distance is higher than 300 meters, levels were at the background, 2, 3 maximum microgram per cubic meter. You see, this is the graph showing the decrease of the ammonia concentration that we measured by this passive radiello sample. And what is the relationship between ammonia air concentration, the concentration of ammonia and H2 in the air, and the abundance of lichens? It depends. It depends on the type of lichens and their reaction to ammonia in the air, of course. If a species is so-called acidophyte, this means that it's sensitive to ammonia. The species cannot tolerate high concentration of ammonia, so they are decreasing with increasing ammonia concentration. There are species which are unsensitive. Unsensitive are not favored by ammonia in the air, so their reaction is neutral. And there are species, so-called, these are important, nitrophytic species, which are stimulated, which are promoted by ammonia. Ammonia, nitrogen is a fertilizer, so it's reasonable that you have more species or several species are more abundant when you have more nitrogen available. So these species are called nitrophytic species, which are increasing until a certain threshold, and above this threshold, of course, even ammonia becomes toxic, and the species start to die in this way. So you have the very different reaction of acidophytic species and nitrophytic species. And you see that this is the photosynthetic cure, the reaction of the photosynthetic efficiency of lichen species exposed to several concentration of ammonia in the air. And you see that the curve of the control species of the background is this. And you see that when you have a very, very low amount of ammonia in the air, you have a stimulating effect. A stimulating effect which is promoting nitrophytic species. It's a fertilizer. You stimulate the algae to be more active in doing photosynthesis. But when the concentration of ammonia in the air starts to grow, you see that also the photosynthetic efficiency starts to drop and becomes very, very inefficient at higher concentration. And this is one paper by my group, which has become one of the most a highly cited paper by Elsevier. We received an award for this. And we have done a study around a pig stock farm about the effect of ammonia emission and nitrogen deposition on lichens. What did we find? So what happened on the pig stock farm? We had that very close to the pig stock farm, we had a lot of nitrophytic species, the vast majority, and moving far away from the pigs, we have less ammonia in the air, and the nitrophytic species start to decrease. Nitrophytic species in red, and the species which are not nitrophytic start to increase, of course. And this was caused also not only by the presence of available nitrogen in the air, but also by the reaction at the bark level. These are tree inhabiting species on the tree board, measured on the trunk of trees. That ammonium, not ammonia, it's a mistake, NH4, on the bark was clearly influenced by the pig stock farm, was decreasing with distance, and in parallel also the pH of the bark was decreasing, moving away from the pig stock farm because of the ammonium. So there is a huge production of ammonia, which as goes through the atmosphere, faces transformation into ammonium, which is deposited over the bark surface of trees, and this causes an increase in bark pH. At the very end, this in turn causes an increase of nitrophytic species close to the source. We can measure this, and we can check what is the effect of nitrophytic species, but we'll go back later on this. Because what I want to show is this is a study in a geothermal area in Italy, the geothermal area of Larderello. Italy has central Italy, in Toscana, where I live, has a long history of production of electricity using the geothermal steam, the hot steam from the ground, and dating back to 1904. So in the very beginning of the 20th century, we had already the electricity produced by this renewable resource, which is accounting now for almost 40% of the electricity produced in Tuscany. And these are geothermal, different types, this is not matter here, of geothermal power plants producing geothermal electricity. And we've done this biomonitoring of air quality around the geothermal power plants. So uh, everything more or less is fine, because if we have a certain worsening around the geothermal power plants, you see in the yellow here, we were especially puzzled by this power plant here, because it was the so-called heaven in paradise. We had tried to give some explanation for this, and we called this plant as benedicted by God, because we didn't have any real explanation. We were, of course, kidding, we were joking with this result, because we tried to say, okay, it's on the top of a hill, probably there is more wind, which caused the movement of the air masses without any stagnation of the air, so less pollution for the lichens and so on. But everything became very, very clear when we removed all nitrophytic species from the calculation of the index of lichen diversity. This is a calculation of the index of lichen diversity with all species present on the trunk. If we removed, we took out the species, the lichen species, which were nitrophytic from the calculation. You see the scale is different. It was recalculated. Everything became clear. There is no need for any benediction from a god for this power plant, and everything now is much clearer. The situation is more less favorable for, to say, the air quality around the power plant. So why this? Because two different pollutants, a cause was we call the mixed soup. One pollutant is causing the decreasing of lichen species. Another pollutant, which is a fertilizer, nitrogen is a fertilizer indeed, cause not only the disappearance of species, but also stimulates the appearance of certain species, so-called nitrophytic species. So we have, with these two pollutants together, if we measure all the lichen species at the site, we have this what we call mixed soup situation that is really unclear. It is better to separate this kind of pollution. And we have published this interesting paper, I think it's interesting, about the pitfall of using lichens as bioindicators around geothermal power plant if you do not understand that you have nitrophytic species which can cause some strange result, because they are stimulated by the ammonia emitted by the power plants, and because of the general deposition of nitrogen from the air. So the story was developed further in a municipality, municipality where I was living 7 years ago, in the municipality of Colle Valdelsa. This is the major urban town there. These are minor towns in this municipality. If we calculated the index of lichen biodiversity on the wall of the municipality using all lichen species present on the trunk, we had this situation. See, very good situation with many blue and green only areas, so it's a paradise. But we were aware that this is not the case, because we know that there is some kind of pollution. We have a huge crystal factory here in Colle Valdelsa, which is known to release HF, which is known to be toxic to lichens. So what happened once that we have removed nitrophytic species from the calculation? A much more clear, realistic picture, you see different scale, of the situation here in the municipality with all the pollution around the urban areas. But we thought that we can use the nitrophytic species, not only removing from the calculation, but calculating another index, the index of the biodiversity of nitrophytic lichen species. So we have another map. And you see here that we have the map of nitrophytic eutrophication, nitrophytic species, where the nitrophytic species are more, you have more eutrophication. This is the map of eutrophication, nitrogen pollution. And you see here, it's clear in Colle Valdelsa, in this area, you have air pollution by sulfur dioxide, nitrogen oxide, phytotoxic gases in general, and air pollution by nitrogen deposition, which stimulate nitrophilic species. Two different types of pollutants causing a different effect here, and the result was the paradise simulated by the use of all species. Of course, this is the case in Italy and in general in Europe, in countries where the sulfur dioxide pollution now has decreased to very, very low level and we have a high concentration of nitrogen in the air. I don't know the situation in India, but probably if this is not the case now, it will be in the future. So try to remember this consideration because you can start to check the situation using the differentiation between all species without nitrophilic species and with only nitrophilic species to check the eutrophication of the study area. And we have started, when we realized that we could measure the effects of nitrogen compounds in the air, we have started to measure the effects in the Mediterranean area in our paper. And it was the first time that we were using pine trees. Why pine trees? Because it's clear that you have, okay, this is another slide. If you have a species with a very, very low bar pH, like pines have a very low bar pH on the order of 3, 4 pH, and you find species which are nitrophilic species which are typical of trees with a very high bar pH, there is something strange. And you can start to measure the effects of nitrogen compounds on these uh, trees in this area. That's what we have done here using pine trees. And this is the typical oligotrophic, non-nitrophytic vegetation, gray, normally that can be found on pine trees. And when you start to see this kind of yellow, Xanthoria planetina, yellow-orange lichens on pine trees, it's a clear indication that there is a sign ammonia effect in the air causing a rise in pH. And we have done a study in another urban area with a source of ammonia here around the hippodrome. There are many horses here. This is a urban park. You see, we have a very low eutrophication here, very high eutrophication, and a very high source of atmospheric ammonia around here, estimated with the use of lichens measured on pine trees. And there is a clear relationship between the bar pH and the number and the index of lichen diversity estimated with the use of lichens. And in general, there is a very, very nice relationship between air pollution in viscose sulfur dioxide level and the diversity, species diversity of sensitive indicators, which can be used in two ways. First, if you have to check the effects of a reduction of the emission in the source, you can say this. If you reduce the emission, and the emission in time in the air of sulfur dioxide from here to here, so you have a great reduction, you have just a very minor, you see from here to here, it's a decrease in the emission of sulfur dioxide. What you have here in the species diversity, you have just a very minor return increase of species. But when you are in the very low part, a very small reduction of sulfur dioxide in the air cause a huge increase of species diversity. So the curve enters in the exponential growth, and a small decrease of the sulfur dioxide in the air can cause a huge increase of lichen species. But this can be seen also going back in the other point. If you are in a very background area, in a very pristine area, in a polluted area, even a small increase of air pollution can cause a disaster in terms of species diversity. So when you have to put an incinerator, a new power plant or something, normally the question is, shall I locate this industrial facility or whatever in unpolluted area or in an area which is already polluted. From the ecological, but just from the ecological point of view, the answer is clear. You have to continue to exploit what is already polluted. Of course, this is not reasonable from a social point of view, because people living in areas which are already polluted can say, okay, I already faced a very high pollution low, so why shall I face an increased level? Place this structure, this factory or whatever in another part. But from an ecological point of view, the answer is clear. And we had used also lichens, in this case, as bioaccumulators. Now we are changing from bioindicators or bioaccumulators. Lichens are like sponge, if you remember from the beginning. They can not only accumulate, not only take up gases which are toxic, so lichen can die, like sulfur dioxide, but if there are elements in the air, like calcium or iron or other heavy metals, they can accumulate these elements in the thallus, in the structure, the tissues, pseudo tissues, and so we can collect the samples, we can collect the lichens, analyze them, and measure the content of these elements. In this case, we have measured and we have traced, you see here, the amount of calcium in this species, in this lichen, Xanthoria palatina, these orange lichens, which is a nice accumulator, and we have traced the impact of a cement plant in Slovakia, in this area, because it's very simple to measure the content of calcium in lichens and to check the impact of cement plant. And if you remember the town that we have measured, that I shown before, where we have measured the quality of the air to lichens in the repeated surveys to time, we have done the same also for the bioaccumulation of several elements. Cadmium in 1993 and 1999, you can see the improvement. Chromium, 1993 and 1999, the improvement is very clear. Nickel, again, lead, and so on. You see, these are the scales, you can check the difference. You see a great improvement in a few years, because this town was very polluted and there's done a big effort to improve the quality of the air. Especially after the ban of leaded gasoline, you see the great improvement. This is the very downtown, the most trafficked area of the city. Probably lead has remained also as dust in the streets, but how lead has decreased dramatically in Italy, in Europe, and places where the use of leaded gasoline has been forbidden after 1992 already, 1993, actually, I don't remember. So what are the mechanisms through which lichens can accumulate elements? Basically three mechanisms. They can trap the particles which are present in the air. They can do some ionic exchange the elements in the ionic form, and they trap these ions outside of the cell. So they accumulate at the extracellular sites, mostly on the cell wall, or the ions can enter the cell intracellularly. This is the proportion of the pollutants which can be actually toxic because enter the protoplasm. So all lichens have the same accumulation mechanisms, these two mechanisms, but the extent of the three ways is different based on the elements and based on the lichen species. There are different approaches, different ways for any lichen species and for any element to be considered. And this is a very nice graph about the accumulation of copper, the proximity of a copper mine in Portugal, and you see the relationship distance from the copper mine is the same if you measure the amount of copper accumulated extracellularly, intracellularly inside the cell, and as particles deposited, simply deposited over the thallus surface. What is changing? You see the scale. Look at the scale. You see the highest proportion is in particles and extracellularly. The proportion of the elements accumulated inside the cell is minimal and can be as low as 5% of an element. That's why lichens can accumulate even huge amounts of metals, toxic metals, without having symptoms of toxicity because elements do not enter inside the cell. So there is no possibility of causing toxicity. And we have tried to estimate what is the amount of particulate matter deposition in lichens. Especially, we have tried to separate the contribution of the most dangerous for the health, the most toxic particles below 1 micrometer of dimension. So we have done what? We have placed the lichens inside a plastic net. We have prepared a lichen bag. In one case, one of these lichen bag has been covered with this fabric, with the diameter was 1 micrometer, and we have measured after 3 months of exposure side by side the difference in the accumulation of lichens in coated and uncoated samples. You see, in one case, expected that, perspective, but the reality, lichens could accumulate only the particle having a diameter of less than 1 micrometer. In the other cases, the accumulation was based on all the particles available in the air. These are the outcome. You see red was the uncovered. You see the difference in many cases, and the blue was the covered. In general, all elements except a few, which are mostly present in ionic form like cadmium, nickel. You see that for many elements, and these are clear, antimony, copper, and also chromium, but even iron, these are typical elements which are released by the abrasion of breaks. Lichens, I forgot to tell that lichens in this case were placed along busy roads, and the measured pollution was from car. Of course, antimony now is the best tracer of car pollution because of the abrasion of antimony particles from the brakes. So a close association between antimony, copper, chromium, and iron, it's and zinc from the abrasion of wheels, is a clear indication of traffic pollution. And you see that everything is higher, of course, in the lichens that were not covered. But we can also measure clearly with this way of using the lichen bags the amount of submicronic fraction of the particulate matter, which is actually the most toxic. Another point is that lichens, when accumulate elements as ions, so extracellular ionic uptake, extracellular ionic uptake, they reach an equilibrium with the surrounding environment. When we do experiment of the accumulation by soaking samples inside solutions with different known concentration, you see that the correlation is fantastic for copper, zinc, but even for a very toxic metal like mercury. So when we incubate lichens, we soak lichens in concentration at different values of these elements, we have a clear and nice correlation with the concentration. So lichens can really be used to indicate what is the uptake of the from the surrounding environment. And then we have done a very nice experiment. I think it's very nice. The results are very positive for us. We have transplanted these lichens, which is called Vernia prunastri, in the botanical garden of the University of Siena, and for 3 months, and we have collected the bulk deposition from the atmosphere in the same period, monthly, and we have compared the content, the elemental content of the lichen transplants and the bulk deposition. And the outcome was very, very nicely linear. You see that we can measure by the transplants, so even at these low pollution sites at the botanical garden of the university where I work, for aluminium, copper, mercury, antimony, iron, and arsenic, we have a clear relationship with bulk deposition. So the lichens can be used very, very efficiently to monitor the accumulation of these elements, also in places where the pollution is low. And then another trendy, let's say, up-to-date way of measuring the accumulation of toxic compounds like microplastics. This is the first paper reporting the use of lichens for monitoring microplastics from deposition from the atmosphere. And we have done the studies around landfill dumping site in Italy, and then found a very, very nice, I don't know if I slides, no, I don't have, very, very nice correlation between the proximity to the landfill and the amount of micro fragments and microfiber of microplastics in lichens. So we are trying to develop now this last point because we have a very long experience about the use of lichens for studying the bioaccumulation of heavy metals, of trace elements in general. And now we start to study, we continue to study the accumulation of airborne microplastics in lichens in Milan, one of the biggest cities in Italy, one of the most polluted in the Po Plain in North Italy. I think this is my last slide. Yes, it is. And hope you have learned and seen how simple is the use of lichens for monitoring the quality of the air. There are some tricks, there are some pitfalls that can be that shall be taken into account for monitoring the quality of the air, but the use of lichens can be very, very useful, especially in countries like India, where you have a high load of pollution, you are developing very, very fast. And so there is the need to monitor not only the concentration in the air with the technical equipment, but also what are the effects on living beings, on humans. And if you have sensitive indicators that can be used, it's very simple to go in a place and check tree trunks. There are lichens or not. So if you see lichens, you can say there are many or just a few, or there are no lichens at all. And in this way, it's very simple to understand if you live in a polluted environment, in a medium polluted environment, or in a nice environment with a good air quality.